Dave was saying, the first couple of minutes, we double check the services. We make sure that the stream is coming in, the sound is coming in. Everything is transmitting to LinkedIn and YouTube. And
Yep,
Dave is going to do a few community announcements before we
absolutely.
dive in.
Well, I see us live on LinkedIn, Vlad. So I'm going to go ahead and jump into the community comments while we let everyone get in. As I said last week, we've got a couple of upcoming events that I'd like to talk about. If you want your event listed as we talk about these, please go ahead and drop me a message, or you can send us an email at hello@manufacturinghub.live. So the first event is Integrate Live. If you guys listen to episode 46 with Alan Ray, he was talking about collaboration and the need to collaborate. And this seems like one of those interesting opportunities. So these guys are going to talk about IIoT, leveraging legacy PLCs with MQTT, and sending operational data to the cloud. It's going to be a super transparent and honest conversation where they talk about pricing, and there's full transparency, and that excites me a lot about this. So you guys can go ahead. So the virtual workshop is March 16th at 11 a.m. East Coast time. We'll go ahead and drop a link for you to go ahead and register below if you'd like to go ahead and hear that. The other one is on March 30th. ISA is having their IIoT and Smart Manufacturing Conference. The virtual conference is going to be jam-packed schedule that I know because I'm part of the conference committee, and you guys should definitely go ahead and take a look out to see what's going on with that. You guys can check that out at iiot.isa.org. And again, I will go ahead and drop that below. And again, if you guys would like us to talk about your event, if you've got something interesting coming up, please go ahead and drop me a note. I would be happy to talk about that. Now, Ilian, this is my fifth favorite part of the show. It's where I get to embarrass Vlad. So you may or may not know that Vlad has a successful YouTube channel called Solus PLC. Hey, Solus. So there are about 28,000 subscribers, which is, I mean, it keeps growing, which is amazing. And it only in part because I continue to ask people to subscribe. Well, Vlad doesn't ask people to subscribe. But here's my pitch. Go ahead and subscribe to Solus PLC if you guys want to watch this live on Wednesdays and check out all of the awesome content and understand what is going on with that amalgamation behind Vlad as well.
Thanks, Dave.
So go ahead
Appreciate it.
anytime. Vlad won't ask, so I will ask. We also have a Manufacturing Hub YouTube channel where you can watch all of the clips and all of that as well. Before we jump in, we want to give a shout out to and thank Siemens for sponsoring this entire robotics theme. And you guys can go ahead and check us out on manufacturinghub.live, where this and the past 51 episodes before this all live in there together. Vlad, before we jump in, do you have any other thoughts?
No, I was just going to add, as always, we do the show live so that there is an opportunity for the audience to come in and ask certain questions. We always pay attention to the LinkedIn and YouTube comments. So if you have anything pertaining to the conversation we're about to have, make sure to post them in the appropriate sections and we'll do our best to respond. If we don't get to respond to every comment, you can usually reach out to our guests over LinkedIn. And again, if there's any links, any I would say additional materials that we discussed, there's going to be links posted on the website as well as the show notes. It's all to you, Dave.
Absolutely. Awesome. Thank you, Vlad. Thank you, everyone. And everyone, welcome to Manufacturing Hub. I'm Dave with my co-host up here, Vlad. We have a very exciting episode today where we're going to continue to talk about our theme, which is robotics. And I mean, who doesn't love robots? So our guest today, Ilian Bonev, is going to talk about a number of things, from his background as a professor to literally the world's smallest industrial robot, which he at some point, I promise, will once again pick up in his hand, and you guys can take a look at it over his shoulder at the moment. But without further ado, Ilian, welcome to the show. Thank you for being here.
Yeah, thank you, Dave, for having me. Thank you, Vlad.
Thank you so much, Ilian. As we always get started, and as Dave alluded to, we'd like to know a little bit more about your background and how you got into manufacturing robotics and where you are today.
Yeah, so I'm a professor at the ETS, teaching robotics, doing research in robotics, and basically I've been at the ETS, which is one of the biggest engineering schools in Canada. in Montreal. So it's a French-speaking university. And I came there like 18 years ago. And honestly, at that time, my research was mainly in parallel robots. So you've probably heard about delta robots, this kind of hexapods, the kind of robots that displace motion simulators, flight simulators. And the way I got involved in industrial robots is really because at our engineering school, it's a very, very application-oriented school. Most of our students are already technicians. And today it's probably not a big deal, but especially 20 years ago, we were really the only ones to have like a very big industrial robot lab for teaching industrial robotics. But even today, we still have like 4 big industrial robot arms and 4 smaller ones from ABB, YuMi Collaborative Robots. So basically, we have a lab with 8 industrial robots to teach students industrial robots. And this is how I got into industrial robots, in industrial robot arms, basically. And eventually, I had big funding to purchase lots of different robot arms from Fanuc, from ABB, from Kuka, Motoman, and so on. And then later, collaborative robots. And this is how I started, doing research into industrial robots. And mostly, this research was about how to make them more accurate. So it's about precision robotics, how to make how to calibrate industrial robots, and but there are different research topics about optimization, for example, how to make optimal use of industrial robots and so on. So yeah, this is kind of my background.
And Ilian, a small side note, I guess, from ETS, there's quite a bit of innovation that came out, and we'll talk about Mecademic in a moment, but there's also even Robotic. I don't know if I would assume our listeners are familiar with that software that's stemmed out of there, right? So there's quite a few, I would say, innovation pieces in terms of robotics that came out of ETS. So it's, again, a very interesting place to be. I personally went to Concordia, so I don't think it's at the same level as ETS from a technical standpoint. So I'm very happy to have someone from there.
So Robotic is basically a spin-off from my lab. It was developed by Albert Nubiola, who was one of my first students working on robot calibration. And but there is also Kinova, who are well known for working on more research robot arms, also medical robotic arms. But soon they will reveal their first collaborative robot. So Kinova is also a spin-off from ETS, and you probably know, if you have kids, if you buy, if you are hobbyist, you probably know the RoboShop.
Yes.
Which is also a big marketplace. It's a big marketplace for robots, for different types of hobby robots. I think you can even buy some smaller industrial robots, or at least industrial robot grippers anyway. And it's also a spin-off from our department at the ETS, automated production department.
Oh, it's really cool. I think, again, a lot of really good innovation came out of ETS. But in terms of, Ilian, I would say, get a perspective from you on how the education in robotics changed, over the last 20 years. So, maybe taking us a little bit back, how did you, or what was the learning curve in robotics versus what you see today? Do you think that, with the advancements in technologies, has it been made easier for students to learn? Has it made it more complex because there's so many different platforms? What is your perspective in terms of educating, I would say, the new workforce on robotics?
Yeah, to be honest, there is so much going on. I mean, maybe for the first, 10 years, I didn't have to update very often my PowerPoint presentation. But for the last 6-7 years, I've been doing it like almost every semester because there are so many new, the collaborative robots, companies like Mecademic, so many, innovations. But at the same time, I would say, yeah, there are different types of robots, but it's still the same technology. So, I still teach inverse kinematics, Euler angles, direct kinematics, that's the same. And even today, I still have to teach those things like singularities because robots are still, I wouldn't say dumb, but they don't. You have to compensate, with knowledge to know how to use them in an optimal manner. So even though some robots today, as I said, my students, okay, I agree. You can buy a collaborative robot today and you don't have to follow my course. You will be able to program it in 5 minutes, but you will be able to do just simple applications like pick and place. But if you want to do something more complex, if you want to use the robot in an optimal manner, you have to follow my course, because otherwise you will have no idea what a singularity is. You will have no idea how to define the, I don't know, the end effector of your, the reference frame, the tool reference frame of your end effector. So, so this will never change. And probably one thing that changed, especially with the COVID crisis, is we use ABB robots, so we use the Robot Studio software. And before COVID, I didn't that much rely on it. But with us being confined for at least 2 semesters, I think, and we kind of let's say used robot software like Robotic or Robot Studio much more. So that's probably something that changed. And today, even though students, they always prefer to come in class and use the real robots, I always tell them that, all these things that I teach, like inverse kinematics and the different configurations, you can easily see those when you use software, simulation software. So you should continue to use this software. So probably that's the main thing that changed for the last years in terms of teaching. So now you can use, advanced simulation software. But the rest, yeah, I still have this almost the same lecture notes. I just have to update them with, new robots that come up. But the theory is still the same.
It's interesting, that you mentioned on that last point that students are a lot more exposed to simulation software. And I think it would be important or interesting at the very least to see the data on how they perform in the marketplace, right? Because on one side, you could argue that exposure to real robotics makes a little bit more sense. But on the other side, in simulation, you can do probably a lot more and be exposed again to a lot of different brands. You can probably do motion that, again, you wouldn't be able to do in a lab. And at the same time, you could probably teach a lot more people. Then again, you can probably not purchase a robot per student. So there's always these, I would say, logistical constraints. But I think it's going to be interesting to see what the feedback from the manufacturers are going to be. I would say, like at the end of the pandemic, hopefully, with the new workforce. But in terms of maybe the transition to Mecademic, what was the and I would say, I guess let's introduce it before we dive into the transition. What are you doing today with Mecademic on that side?
In terms of simulation software?
No, I would say in general. So could you maybe give us a little more information as to what Mecademic does and provides?
Yeah, sure. So basically, Mecademic was I had the chance to meet this brilliant student, Jonathan, who is the CEO of Mecademic. And initially, he had a very unorthodox background as a machinist. And then he came to ETS to pursue a degree in electrical engineering. So he already designed robot arms in his past time and so on. and I hired him for designing different parallel robots, which was something I was doing. And so the first product of Mecademic was actually an educational parallel robot, which was really very, very original. But we very quickly saw that the market is very small for educational robots. And also at the same time, I must agree that, you might, teaching students, you might as well use robots that are actually present in industry, not some kind of invented robots, which are interesting to study, but they don't have a direct application in industry. So, and it was also Jonathan's dream to design a real 6-axis robot. So, yeah, I agreed with him, even though at the beginning I thought like, wow, that's so ambitious. How can you do something better than all these companies that have like almost 50 years of experience? But then I saw he came up with this little guy, and I changed my opinion very quickly because, of course, the first prototype was not perfect. It had bugs. It was, but even though it was not perfect, it was already so much better than other robots in terms of compactness. It was extremely compact, extremely precise, of course, because it uses the same technology as bigger robots, but it's much smaller, like harmonic drive gearboxes, speed reducers. And so very compact and very, very precise. And then since Jonathan was, he had this background as a machinist and electrical engineering, and he was not kind of overexposed to the current industrial robots in my lab. And so he had like a new vision of how, industrial robots should work. And at the same time, I told him, the minimum of what an industrial robot should do and so on. So then we came up with this third advantage of our robot, which is not only small and precise, but also kind of as a component, easy to use. Not the same kind of easy as collaborative robots. Like you cannot program everything from scratch, but it's easy in the sense of a component. So you just plug it to a laptop or to a PLC, and then use the kind of programming language you are used to, or even the kind of communication protocol you're familiar with, and then you just use a set of commands to make the robot move. So you don't have to do all the inverse kinematics or whatever. It's still the same as a typical industrial robot, like move, lean, moves, joint, and so on. But all the other logic, like if, then, else, and so on, you do it in your programming language of choice, and you don't have to learn, a whole environment. Like in the case of robots, it's not only the programming language; it's also the teach pendant interface, the software you need to install on your PC, and so it's kind of like really a component, motion component. It's still a robot. It still has all the motion planning and everything, but it's kind of is all the essentials, and that's also something which is at the same time, it's normal. When a company starts, they don't start with everything, and they start from the beginning and then add stuff. But we are very, very careful not to add too much layers of stuff, because that's the way, other industrial robots became so complex to use, because, every time a client asks for some feature, oh, I would like to do this, I would like to do that. So you add, then you come up with an idea, oh, let's do a 7-axis robot. But then, oh, we never thought about how do we control the 7th axis? So let's put it in this variable, even though it was not designed for this. So this is how industrial robots today became so much complex to use, because I remember when I started teaching, we used very, very old Fanuc robots, and they were easier to use, So, I guess it's kind of inevitable, after 50 years of adding stuff. But we are very, very careful about, what we add to the robot. And sometimes, we know, okay, I know this is very, very useful feature, but if we add this for 1% of our clients, it will make life more difficult for, 80% of the clients. So we'd rather limit ourselves than make, all whistles and bells and add those.
And Ilian, if I may follow up on that, I'd be really curious, because I think very few people have I would say, the privilege to go through the design phase of a new robotic arm nowadays, right? And so looking at someone who has, I would say, seen integration projects, and I think a lot of our audience has probably been involved in programming different robotic arms, and some probably realize the complexity that goes into a robotic arm. But I'm curious to hear from you, what were maybe the top 3 challenges in that process? And it could be, again, it could be on the software side. I would assume sourcing the right materials is going to be also different. I believe Mecademic also manufactures the ARM components, right? Like in Montreal. So I'm wondering, what were again, the challenges designing a robotic arm from scratch in that way?
Yeah, well, yes, you're right. We're basically one thing that sets us apart is that we design and we manufacture most of the parts here. Like, of course, the casing, everything here, it's machined. We don't hear it right now. The machine is stopped, but it's we have like 3 machine tools. One of them, it's a really very complex 5-axis machine tool. It's like almost 1 million, I think it costs, with a SCARA robot that displaces the jigs and everything. So we do, and we are based in downtown Montreal, which is very, very, special. So we machine the parts. We even do the electronic cards. We assemble them next door, like literally 5 meters away from me. And we develop even the drives of the motors. So most of the things are developed by us, and everything software-wise. We don't buy libraries, even stuff like, I don't know, Profinet or EtherCAT. We design everything from scratch, even though you can easily buy, this and pay a license fee. So yeah, these are the challenges, because we have to develop everything from scratch. Otherwise, I would say for me as a professor, I was never involved in, for me, it's like, oh, you do the inverse kinematics and that's it. But no, there are so many things like path planning and so many different layers of, I'm not even aware, like I've been involved a little bit in the web interface, but that's nothing like compared to what's inside the controller. It's even for me as a professor, it's like a black box. It's the R&D team, we had to discover this. Nobody in our R&D team had any experience with building robots before. So we had to learn by ourselves, and that's definitely challenging for a small team. Yeah.
Absolutely. And I would assume that there's probably not that much open source information, right, on designing robotics, because I think a lot of these companies, obviously, once you design it, you want to some degree, keep it in a private space. So I don't think there's that much you can leverage of existing information. Dave, before we go down the technical path, as I have many more questions, is there anything you'd like to chime in on?
Absolutely, Vlad. I appreciate it. And so, Ilian, I love as you kind of like talk about the path. So Vlad said that he had met you guys at Mecademic a number of months ago, and you guys have this tiny robot. And my first thought is, why would anyone buy a tiny robot? Like I when I think of robots, I think of the big, orange Kuka Titan, right? Or the big white Mitsubishi welding robots, something like that. And then last week we had a very interesting conversation with our guest who talked about lots of people using cobots because they're smaller and you could run them with less kind of safety equipment and you could fit them in tighter spaces. And I feel like this is a very interesting conversation. And I'd love to know more about some of the applications you guys find yourselves in. Like, so you were just picking up the robot as we were talking. And it seems like yours is the robot that if I have an existing application or I need to move something, but I don't have very much space, you guys are who I would use. So what sort of interesting applications does Mecademic find themselves using because your robot is so small?
Yeah, so it's really by chance that we came up with this idea. It was like, honestly, we were still at the ETS and Jonathan wanted to design a robot. And so, of course, it's easier to design a small robot than start with a big robot. It's cheaper and the gearboxes, everything was more affordable. But then once this was done, we were like, wow, it's if you go to my lab and then look at all these robots, even the smaller ones, they still have these big controller boxes, like a big desktop PC, and then big cables, and then big teach pendants, and then sometimes for many applications it doesn't make sense because you just kind of displace small screws or small pinions or whatever for the watchmaking industry, and you can probably fit this big robot, but it just doesn't make sense, because usually in all these applications where I see our robots, I don't really see how they fit like a bigger one, and it's more. I would say our competitors are not bigger robot arms. It's really like custom-made linear guides, a couple of linear guides with some rotary stage. So it's they don't have, like, people, they don't have space. So what kind of examples? I mean, the applications that our robots do, most of them are not very nothing very, very original. It's just small parts. Like, let's say instead of palletization, you displace dental implants or catheters, or for the watchmaking industry, very, very small gears. It's not called gears, but yeah, something like this. And yeah, of course, from time to time, we have some very original applications. Like, for example, NASA is trying to use our robot for micro manipulation of extraterrestrial samples, like basically dust, or I don't know, Mars, lunar rocks, whatever. Or we have our very, very first client was actually a Montreal company that uses the robot for microsurgery of lab animals.
Interesting.
But most applications are very, very simple. I mean, simple. I wouldn't say simple, but very. It's challenging because they need precision and everything. But it's if I show it to somebody who is not in robotics, they will say like, "Oh, what's the robot is just moving stuff from point A to point B." It's not like rocket science or whatever. But it's in all these cases, you cannot have a human operator because it's really like a very, very small cell. Like in watchmaking, it doesn't make sense. Somebody sitting and just putting these small gears in a like kitting operations, so it's yeah, just small products, just displacing very, very small parts. Instead of having a bigger robot, you have this one, which is very, very compact. So that's it. That's the main It's as simple as this. They buy it because it's very small.
And I like the
That's
example, before I let like Dave jump back in, I like the example that we talked a little bit off stream, which was the lab work, right? So the robot handling some kind of like a chemical or like I guess a biological sample, and can very precisely and again repetitively, I think, perform a
Mhm.
task that can be going on for multiple hours, whereas again a human would not be as precise and would probably not want to do something of that nature, or even be capable of doing that for long periods of time.
Mhm.
But no, I think those are really good examples. I think we don't necessarily intuitively always recognize that just
Mhm.
based on the size alone, but they are accomplishing tasks that need to be done. Sorry, Dave, go ahead.
No, no, absolutely. And kind of to both of your points, I think that removing a lot of that manual manipulation is a huge positive, because I know many people who have worked at factories for a decade or a couple of decades who have like lots of carpal tunnel issues from that same repetitive motion. So if we could go take, you know, a couple of these robots, or a couple of any robots, to be honest, and remove all of that manual manipulation and allow a human to use their brain, what we should hopefully do a better job as humans over dumb robots, then it should be a win-win for excuse me, it should be a win-win for everyone. But Ilian, so you made a really good point talking about how kind of your major competitors are not necessarily other robot manufacturers. It's people who have kind of made their own, right? Maybe we've got a couple of axes, and then we've got you know, a couple of grippers. I'd love to kind of hear your thoughts, both. I mean, maybe from the academic side, right? Like as a university professor, I imagine that you've seen lots of robots. I've imagined that you've designed a lot of your own. Kind of what are your thoughts on purchasing a this will work most of the way versus let me custom make a couple of access thing exactly for my job?
Oh, yeah, that's a very good question. So it's um, basically I had at least two, or no, actually three different situations where I designed these. Well, at DTS, well, at least I had a lot of funding, so I could build robots which were really very precise and well made, with lots of students. And in at least two cases, we ended up with some very complex robots that was specifically designed for a given application. Like once was for well, it's for echography of patients, and it was made for the lower limbs, for the legs. So everything was designed specifically for that. And at the end, the robot was kind of flexible, and it was very expensive. So in that case, for example, I just ended up buying Kuka's Iwa robot, which initially seemed like extremely expensive, but then I said it's way cheaper than this monster that I designed. And at the end, you get something which is very precise for the task. It has force control already, and you can program it in Java, so it's perfect for research. And so this was one example. Then the other was we designed this very strange parallel robot, which was very optimized to have a simple kinematics and so on, and with a big back-off controller. So everything was perfect. Machined on 5-axis machine tools, everything optimized. And then it was flexible, very flexible, and it was huge. And then honestly, its workspace was smaller than this guy here. It was less precise, much less precise, and it costed probably, I don't know, at least 5 times more than a Mecha 500 robot. And so I kind of, you know, I gave up, and I said, wow, you know, it's much easier to just buy commercially available robots, even though sometimes they seem over designed for the application. and then you just improve them. Because that's the other good thing for me as a researcher, is that industrial robots are kind of, they have high performance, like very precise, very fast, or whatever, very compact. But as I said, they are, you can calibrate them to make them more accurate. You can do optimization to make them more intelligent. So there are lots of ways you can improve them. And so I can still do research, I can still improve, but it's so much more affordable to just purchase something off the shelf and then improve it, or even use it as it is. Like we have so many applications. You look at this, and it's like the robot is just picking something and then putting it here. It's like 3-axis motion. And it's like, oh, why did you buy like a 500? But then, why? Because I just bought it. It comes in a small box. It takes like 1 week, no, maybe not even 1 week, 2 days to deliver. You plug it, you program it with whatever programming language you want, and that's it. Now imagine if you had to design this by yourself. You can do it, but it will definitely take months. And yeah, okay, if you have like 100 machines, it's probably worth it to design something specific. But if it's only for 2, 3, 5 machines, it's even though you only need 3 axes or 4 axes of motion, it's still more affordable to, at the end, to buy something that seems, over designed. And just program it quickly, and that's it. So yeah, industrial robots, 6-axis robot arm. It's not. When I teach my students, and I always tell them, these 6-axis robot arms, it's like it's about 60% of industrial robots are 6-axis robot arms. It doesn't mean that you always need 6 degrees of freedom. It just means that it's always just better to buy a 6-axis robot and then use it as a 5-axis or 4-axis than to, sometimes I even show my students like 5-axis robots. And then I say, why people buy these? Because you only have 1 or 2 models of these, and you probably don't even save money, so why not just buy a, like sometimes you've probably seen these big cooker robots, 6-axis Titan robots, they do just palletization. So I say to my students, well, why do people use them for palletization? Because there are no palletization robots that can lift 1,000 kilos. So that's why it's cheaper to buy something that seems over designed than to ask to design like a 1,000 kilo palletization robot.
Yeah,
absolutely.
Go ahead, Dave.
I was going to say absolutely, and just to kind of add one point to what you were saying, Ilian, is as we call it, kind of like tech debt. If I'm going to go design something as a one-off, that means hopefully I'm always at the facility, because when it breaks, there's 1 or 2 people in the entire world who are able to go fix that thing. Maybe at 100, to your point, it makes sense to design and produce 100 and then train everyone to that. But I would say maybe not all, but nearly every single prototype line, or we bought the first of the kind of the line that I have seen in industry, everyone always has problems with it because they haven't worked the kinks out. So if you only need 2-axis, but you can go buy a 6-axis robot for about the same price, and you can program it, then it's going to work. And if there's an issue, then you can call on 60% of the industry that deals with the 6-axis robot, as opposed to the one person who built for nearly the same cost the robotic cell that you currently have.
Yeah.
And Ilian, as a follow-up to that comment, I think it's interesting to also discuss optimization, because I think you've mentioned it a couple of times, but in many instances of robotics, and again based on my experience, what I've seen in food and beverage, is that you can probably get, I would say, 60 to 80% of the way with a very simple solution, right? So you can probably move a box from point A to point B, but a lot of time, and I would say a lot of effort, is required to get it to where you have an optimized process, and that can play a huge role in like a manufacturing process. And again, I know that Dave has a continuous improvement background, and he probably has a ton of examples of this. But from the robotics standpoint, again, you want to reduce that, let's say, transition time. You want to make sure that everything is programmed to the point where that's not your bottleneck in the system. I was wondering if you had some more thoughts or even examples of optimizations that you've seen in your
Yeah.
area.
So it's I don't know what kind of percentage of applications are very simple, like just handling stuff. But even if it seems like handling, unless it's really only from point A to point B. But even from point A to point B, if it's machine tending, you don't need to optimize too much, because the tending part, it's like, I don't know, 1% of the whole cycle time of the production cycle time. But for many other applications, even it's always from A to B, you can still, because as I tell my students, industrial robots are not six-axis robots, are not Cartesian robots, which means they are not homogeneous. You know, their performances are not the same. Like their workspace is six-dimensional, and in the different parts of this workspace, they have different properties. So from point A to point B, if you do this or this, it's not the same cycle time. But you know, of course, robot manufacturers, we want people to think that industrial robots are as simple as, you know, especially robot manufacturers. They will say, oh, you just press here, and then you teach here, and then you teach here, and that's it. Which is okay if it's machine tending, but if it's something, you know, more critical, you need to do more than just teach here and teach this. Because and I show this to my students, you know, if you decide to pile your blocks, because we just pile blocks here instead of here, then if you put 2 blocks, it works. But then if you put 3 blocks, then the third block is the robot is near a singularity, so it's kind of very slow and so on. So it's you really, if you want to optimize the cycle time, you need to do a lot of trial and error. Unfortunately, you know, for most engineers, they don't have the right tools to do this optimization correctly using, I don't know, genetic algorithms or whatever. But at least I tell my students that you should be aware, and you should at least, especially now with simulation tools like RoboStudio or even Robotic, you can simulate. So just you know, discretize your workspace or whatever, and then simulate where is the best, where you can get the best cycle time, or where the robot is most rigid. For example, if you're doing machining with the robots. And to give you probably a couple of examples where I needed to do a lot of optimization, complex optimization, which was more like master student level or even PhD student level. So for example, one example is somebody was manufacturing masks for military personnel. And so they're doing dispensing, you know, with a robot, but with a single 6-axis robot, it was impossible. So you had to either, even with a rotary table and a 6-axis robot, it was still very difficult. So imagine if you have this kind of application, if you don't optimize, you will probably end up buying 2 robots instead of just 1 robot and a single rotary table. So it's more expensive. And also, it will probably be it will probably be slower with 2 robots instead of 1 robot and 1 rotary table. Another example is a company that was doing inspection for the aerospace industry. So basically, you have this scanner, 3D scanner, and you have to inspect the part in, let's say, 20 different orientations, okay? So the way they used to do it is just random. It's 1, 2, 3, 4, 5, 6, 7, 20 times. But then it's similar to the traveling salesman problem, where you have like different cities and you have to visit all of them, but you need to optimize which is the best trajectory. So the distance traveled is minimum. So it's the same here. You, instead of doing this and then this and then this, if you do an optimized sequence, then the cycle time will be much faster. But it's
so you reduce the movement time between the points, right? Essentially.
Yeah, because from here to here, it's a waste of time. You're not making any money. And it's even more complicated than traveling salesman. So let's say it's more like a traveling politician, which in every state has to visit at least, not at least, but he has to visit one big city. Okay, so the politician has 2 or 3 cities as a choice. So what are the equivalents in robotics of the cities? It's the different configuration, because you can be like this, or you can be like this, or you can, these are the different solutions of the inverse kinematics, the configurations. So it even becomes more complex, but with these different configurations, then you are even more optimal. So that's another example of how you can, then another one is machining. So in machining, you only need 5 axes, but the robot has 6 axes. So how do you manage this redundancy in order to avoid singularities, for example, or to be more, or just to be able to do this? Because, people, it's easy. If you cannot do this, you just buy a bigger robot, so you can do it for sure. Like a huge robot will definitely be able to do the mask dispensing I told you about, but it just doesn't make sense. You will not end up buying some huge robot for, I don't know, $150,000, while you can do this with a smaller robot, but you need to spend more time, optimizing the workspace and so on. So yeah, optimization is even more important for guys like at Mecademic, because the robot is very small. So so sometimes, clients, they ask us, oh, do you have a robot that is 5 centimeters bigger? Tell me what's your application, and I'm sure I'll be able to, fit it in. It's not like, or the worst is, and I tell this to my students, like people who ask us, oh, what is the reach of the robot? It doesn't matter what's the reach, because it's your application is not just doing this, it's doing this and this and that, and this, you cannot describe this with a single number. So you have to simulate in software like Robotic. And Robotic, by the way, this is very interesting, because in Robotic you can use different robots and you can compare, okay, with this one I can do my task, and then with a bigger one I cannot, or vice versa, and so on. So yeah, use simulation software, and it's always better to use the smallest possible robot, because it's more affordable, but it takes less space, it consumes less energy, the controller is smaller, so it's easier to do anything with a bigger robot, for sure. It's like having a truck. It's easy to transport stuff, but nobody buys almost nobody buys a huge truck for going on vacation from time to time. So you kind of optimize, okay, I'll buy a smaller car, and whenever I have to go on vacation, I'll probably put a box on my car. And so yeah, you need to optimize, otherwise you end up buying a truck every time you need to move something.
Ilian, let me ask one question before we dive into this, to thank our sponsor. But I picked up on one important point you've made, and that's at the beginning of the statement, which was that a lot of times these optimizations would be done by masters and PhD students. I'm curious, Again, obviously, obviously you can learn those skills, but what are they on top of, let's say you learn the software, you learn how to program a FANUC robot, or you learn how to program it in Robotic in a simulation, for example, and you have I would say, a general understanding of, I would say, mechanical applications, right? Like, what are the skills that you see, or that you teach at the master's and PhD level that would make them, I would say, above and beyond what you would typically expect, like before that? What I would say, what clicks in, let's say, if I was to program these robots, what would need to make sense to me to understand how to optimize a lot better than otherwise?
Yeah, so well, it's on the website of Mecademic. I have this section called Mecademy, where I kind of make tutorials about singularities, about Euler angles, quaternions, workspace, and so on. So this is the minimum, like at least people should be aware of these limitations of robots, because again, 6-axis robots, unfortunately, they're very useful. They have huge performance and so on, but they have singularities. They have limits, and so the minimum is to understand those limits. And then if you really want to optimize the robot, well, it's at least you can do it just by discretization and then a lot of trial and error. So this is the list you can do, like just be able to use some kind of software, simulation software, for example, in Robot Studio, but I think you can do it in Robotic. But in Robot Studio, one thing I love is that it's been there for many, many years. You can use this virtual reality headset, and then with the controller, you can grab the end effector of the robot, and then you just kind of move it in the virtual space, and you can see if the robot can do this or not, which you can do this with some collaborative robots, but it's not the same because it's kind of more force, it's a bit more difficult. So yeah, just do it by simulation. And then if it's really important, then yeah, you need to learn different optimization techniques. These are just available as open source. Like for example, if you want to do this by genetic algorithms, you can have a library in Python or in MATLAB. So you don't have to be a specialist in everything. But other stuff, like if you want to calibrate your robot, that's yeah, you have to learn different skills for this. But it's more, yeah, it's definitely graduate level. So it's not something you can learn by yourself. Yeah.
That is interesting. So I actually have a couple of comments on that. So we brought up a bunch of really good conversations on simulation. So if you guys are interested in learning more about simulation, especially simulation on robotics, go back and listen to the last episode 51 with Max Kirkpatrick. Max works on simulating robots and robots within lines. And so we had a bunch of conversations around what he's doing there. So I think that is absolutely worthwhile going and having that conversation, or going back and listening to that with Max. And then talking about optimization, I think we brought up a lot of really good points. Enough points that we could certainly fill more than an entire episode. I will just bring up a couple. So when I go out and I look at robotic cells, without saying kind of everything needs to be optimized, I like to go look at them, right? And so you can generally see, kind of as Ilian was saying, if robots are efficient or not, right? So like, obviously, if my robot in the middle of its cycle, like flips all the way to the backside and like twirls around a lasso, we know that it's inefficient. But you can also see that sometimes there are a bunch of additional axis movements that it appears to be hunting, or at least what I would call hunting, right? Like it can't find where it needs to be, and there's almost like a hitch in there. And so I would say that is a good opportunity to look for hey, how can I make this more efficient? I'll give one quick example before we move forward. I made this comment to Ilian yesterday or a couple of days ago. So I had a client that they make tools. I was playing around with my tool, or I was playing around with the carabiner, kind of similar, right? So it goes through a line, it gets heated, it gets quenched, it goes up a belt, and then there are these five robotic arms, and it was maybe the most inefficient robotic cell I've ever seen in my entire life, right? All of these arms are constantly hunting. The belt was way too wide. I mean, I could probably list 20 things that was wrong with it. But the main point is, like, I go and watch it and I capture, a minute of video, and I go, and as I continue to go down and watch, every single one of these robotic arms just grabs kind of whatever tool they find coming down to go through the next process. So as you go through, especially if something is your constraint, if you're looking at a robotic cell, you'll certainly see if there are issues with optimization kind of within that cell. And as we've discussed, and we'll have to have more conversations on at a later date, optimizing, like, people want robots, absolutely. I'm not sure I've ever heard of conversations as to, are my robots optimized? Like, maybe it's, can my robot hit the cycle time that I'm looking for? And as soon as we can check that box, we're done. But just because we check that box doesn't mean that we have optimized the robotic arm in and of itself. So I think all of those are very good points. Thank you for that, Ilian. I'm going to let Vlad go ahead and play that note, and then we're going to go thank some sponsors.
There you go, Dave.
Awesome. So we once again want to thank Siemens for sponsoring the robotics team. Before we jump into this, what I was thinking about when we were talking with Max last week, and this is, Siemens is just one of those companies that, like, seemingly does everything, right? And so the technological tasks in modern machines and plants are diverse and often demanding. It's good to know that there's a smart answer to all challenges regarding motion control, signal acquisition output, closed loop PID control, edge computing, artificial intelligence, and machine learning with SIMATIC technology and the SIMATIC Technology-CPUs. Siemens is the global leader and innovator when it comes to industrial motion, robotic, and simulation applications. Simulation, once again. They are one of the world's biggest investors in technology R&D, spending more than $6.11 billion per year, which, once again, we just have to take a moment and think, that's a lot of robotic arms, right? Like, even at $100,000 a piece, that's a lot of robotic arms. And they have maintained this investment throughout the pandemic. So the integrated and scalable SIMATIC technology automation solutions save you valuable engineering time for simple tasks as well as for complex issues, and guarantee maximum efficiency and flexibility. This means one engineering framework portal, one with Siemens Technology CPU, and one communication for standard automation, safety, and motion control with Profinet. So I'm going to go ahead and let Vlad point to all of the Siemens currently behind him. But it's one of those things that it's, if you are working within the ecosystem, any ecosystem, it's always nice to have something that just as seamlessly as possible in this industry goes ahead and connects with it. Again, we want to thank Siemens for the support of this theme and the continued support of the community and their show, and this show. And Ilian, with that, I kind of want to, like, jump in. We talked a lot about optimization. I think that that's a very interesting future-looking opportunity. Can we kind of get your like, where do you think, what is the future of robotics going to be?
Yeah, I think the next level is, like, how to make robots more intelligent, optimized. But honestly, I don't think this is the job of robot manufacturers. I mean, we definitely at Mecademic, we definitely we work on features that make our robots more like more intelligent, if you wish. Like, for example, one example is most industrial robots, if not all, they don't check for mechanical interferences. So you can just job them and they will hit themselves. I mean, that's something that can be avoided, or like if you have a 7-axis robot, let's say, and then you you tell the robot to go to a 6-degree of freedom pose, then the robot, optimize itself for the 7-degree of freedom. So there is some kind of minimum that robot manufacturers should do. There's still a lot of possibilities, but then it's really up to third parties to design software that will take, information from cameras or whatever, different sensors, and do the optimization or real-time optimization. Or if it's not real-time, then probably you can use software like I've heard that Siemens' software for robot simulation, it has some advanced feature on optimization. But again, there's no software that can do everything. And I even have an article about this, like artificial intelligence, like there will never be, some kind of super powerful computer that will kind of always find the best motion from point A to point B, because it's really the installation as well. It's really when you design the robotic cell, the whole, it's there that you need to optimize. It's not only the robot. So even if the robot is very intelligent, if you put the conveyor very far from the robot, you still get a very slow cycle time. So that's why I say it's not the job of robot manufacturer to make everything better. It's really the integrators or software that makes simulation, software that makes real-time optimization, like picking parts at Amazon warehouse. Obviously, again, you need some kind of third-party software for this. So I think most of the innovations will come from this, and robot manufacturers will continue to make robots which are faster, smaller, more precise. But then again, robot manufacturers, they don't make drippers, they don't make cameras, so innovations will come from other companies as well, third-party integrators or
Interesting.
software.
Now, do you think that the large robot manufacturing companies will be willing to accept this additional optimization into their ecosystem? Or do you think that we're going to see a fight from companies who already have robotic software and want to potentially add that on to what they have for an additional fee?
Yeah, like if I take Robot Studio as an example, there are some features which are really advanced, like you can model the cables. There is even a physics engine, you can drop parts and see them bounce and everything. But in terms of optimization, that's something that's still missing, I think. Well, I know for sure. And so, yeah, some companies that have this kind of software will probably add those features, but then again, you cannot do everything because there are so many different case scenarios that you cannot think of all different, like it can be as simple as, when you put a gripper, how do you design, where do you put the gripper? Is it here or here or here? So how can you do this in Robot Studio? I mean, Robot Studio is not made for, designing the base place of your gripper. So things like this, you will never see this in general purpose simulation software. So yeah, I don't think robot manufacturers will address too much these optimization issues.
I was curious, Dave, do you have another question before I jump in?
Go for it, Vlad.
I was curious, from a workforce standpoint, right? So right now, I think we're seeing more and more manufacturers trying to optimize their processes because, again, there's I would say, a lack of general workforce, and they're trying to automate a lot of different components of their business. Are you seeing, I think it's going to continue at least in the short term, but do you think, again, in the long term, we're going to see more and more exponential growth of robotics? And do you think it's going to, I would say, with the advancements in software, do you think that's going to require, I would say, more people on the higher end like skill set, or more people on like technician and kind of maintenance level? Where do you see that dynamic play out in the manufacturing space?
Yeah, honestly, I think like all the low-hanging fruits, they've been already picked, and we've seen a lot of robot sales in Asia because there are so many simple applications, but eventually, all these applications that remain to be automated, they are more complex, and you really need engineers for these applications, like integrators, designing. Like that's not even something we teach at university, because it's so much based on practice, how to design an automation system, how to choose the gripper, how to choose the conveyor. So it's not about being technician or engineer, but it's being somebody with a lot of experience. So I think we'll see more and more robots. Probably not exponential growth, but obviously, automation is the way to go. It doesn't make sense to do all these tasks manually, and it's not about stealing jobs. We lack people to like in some places, they closed the Canadian Tim Hortons. They closed it at 3 p.m. because they don't have personnel.
Yeah.
So it's yeah.
I think that's not always, and that's last point, that's not always well portrayed by the media. And I'd say sometimes the old image is that robots are taking jobs, but a lot of times it's, again, even in manufacturing, they simply cannot find enough operators to operate the line. And I think if anything, it just gives people the opportunity to do something different. And it's, again, I think it's slowly changing, but we still have that perception of robots taking a job of someone. But as you said, again, it's certain jobs that even from like a smaller robot standpoint, it cannot be done by humans, I think, and it's not replacing humans. It's a lot of times just replacing other processes that are a lot more expensive and more complicated to figure out. Dave?
Yeah.
Absolutely. My only other comment to that is closing Tim Hortons is an affront to the entire nation of Canada. That is worst case scenario right there, folks. How are you going to get your coffee fix? But no, exactly. So I think that you brought up some very good points, Ilian. And I think one of your points was we basically need a lot of experienced people that can actually go and install and implement these. And unfortunately, we can't snap our fingers and have a lot of experienced folks. So we need to bring inexperience and maybe mid-career. I understand automation, but I don't understand robotics into robotics. So do you have any career advice for those, either people who have seen some robots and think they're interesting, or maybe they've got some experience on the industrial side and are looking to get more hands-on knowledge?
Well, yeah, it's I think nowadays there is a lot of colleges that teach industrial robots. I think it's more and more important to have hands-on experience, not just theoretical experience. So whatever it's vocational training or university, it should be as hands-on as possible. You should always teach the theory, but the theory itself is not enough, because even like integrating a robot, the theory is good for like optimizing stuff, but like poor choice of gripper technology, you can lose, I don't know, several weeks just because you didn't choose the right gripper. And this, it's not something that you learn in a book. You really have to have experience for this. There's no, I always tell my students, when you choose a car, you have all these, is it in English, guide de l'auto, guides for,
car guide.
Yeah, But when you choose a robot or a gripper, there is no such thing. There's no website that
No.
gives ratings on robots or grippers. So how do you choose this? It's based on experience, based on making errors. So, and I'll close with one example. Recently, the technician who is responsible for our robotics lab at the ETS, he retired. And we had so much trouble finding somebody to replace him, even though having a secure job at the ETS with pension fund and everything, it's really like it looks like a dream job, but it was impossible to find somebody there. So there's so much we need people with this kind of training everywhere. I mean, the industry, it's so many applications.
No, absolutely. I think that that's some good advice. I will say it seemed like a lot of colleges and universities have hands-on experience. Max from last week was talking about the University of South Carolina, and he had in his background, they had 4 or 5 or 6 different robots that were kind of within one large cell that they were able to put together to get some of that good hands-on experience. So I appreciate that, Ilian. So last couple of questions to wrap up. Do you have, so I know we talked about Mecademic, I think you called it, where you have a bunch of, or Mecademic Academy, where you've got a bunch of information where you've written about. Do you have any other either books or kind of posts or videos that you would suggest people take a look at, either personally yourself or things that you enjoy to read and consume?
I would say watching YouTube videos. It's not easy to find them because there are so many YouTube videos which are not really interesting, but at the same time there are so many applications with robots that you can learn just by watching them. Like one of my former students, Jeremy, who is application engineer at Robotic. So he teaches the robotic cells optional course in my university, and he has this kind of list of videos. And just watching those videos, you learn so much from somebody has designed. So, sometimes it can be like. Look, by using this kind of mechanical intelligence, the person was able to use a simpler robot than using a camera. And so that you cannot read this in a book. It's like once I saw an application with our robot, which was basically, they were just doing this in a bunch, in a bin with different parts. And until they succeed gripping apart, and they have a camera and check it. So, instead of having something very sophisticated, they were just trying 1 or 2 times until they get the part. So this kind of, mechanical intelligence you cannot learn in a book. So it's really, by experience. Absolutely. watching YouTube videos. It doesn't seem like a very good advice from a professor at the university, but you can learn more from this than reading a book, a textbook.
I like that, Ilian. Would it be possible to get that list and we could attach that to the show notes? Could you provide us with that list, and then we can go ahead and attach them if people are interested on specific videos?
Sure. I'll ask Jeremy. Yeah.
Awesome. Fantastic. Thank you for that. And then the last question, you've been such a fantastic guest, is who should reach out to you? Who do you want to talk to? Who do you want to connect with? Who should reach out to you?
Well, as a university professor, as I said, I work on everything related to precision robotics. So how to calibrate robots, how to make them more accurate. And as a co-founder of Mecademic, of course, everybody who needs like place, parts, or a tool in a very, very restrained, confined space, well, we have our support team, which they can try, if the application is doable or not. And if it's not doable with our robot, we always recommend, other robots or other technologies. So it's if we cannot do it, we just we always try to help. It's not yeah, even if it's a competitor. As I said, our competitors are really like custom-made machines. So if the only way to do it is by custom machine, that's it. Yeah.
No, perfect. I appreciate that, Ilian. We appreciate everything. I'm going to cut flat off before he asks another 3.5 hours worth of questions and save everyone's ears until next week. But no, guys, this has been episode 52 of the Manufacturing Hub with me, Dave, and this guy up here, Vlad. We want to thank everyone for being here. We want to thank Siemens for sponsoring this theme. If you have not already, please go ahead and give the thumbs up. Please go ahead and subscribe to our channels. Please go ahead and subscribe on podcasts. If you guys are listening to podcasts, it helps. And you guys can rate us on Spotify and Apple Podcasts and Audible now. If you're one of the 3 people that listen to podcasts on Audible, then we can have one of the 3 ratings on there. Until next week, we want to thank you guys. Thank you guys for being here. We'll talk to you soon. Thank you.
Thank you, everyone.